Hi, I'm Liam, and this talk is about building a regional service provider network in the North Island using SDN, chorus exchanges, and various network virtualization technologies. I guess first a brief introduction. Telecommunications is my hobby. I actually have a day job that pays the rent, and networking and telco is something I kind of dabble in my spare time and weekends, along with a few other endeavours. Although, having said that, at this point my hobby now has office space and a payroll, so yeah, maybe it's not quite so much of a hobby anymore. So in the second half of last year, I had the opportunity to build a service provider network for providing primarily chorus products like DFAS, UFB, ADSL, and VDSL. Yeah, why and how? There are a number of favourable factors that made market entry possible to smaller players in the last couple of years. The chorus bond requirements have come down a lot. Previously it used to cost you about 50 grand, and it's actually come down again since we started. I think now the bond requirements are around 10 grand. I think for us it was somewhere in the middle. Chorus released USB tail extensions. New Zealand has, I think, approximately 33 USB areas and 24 chorus. Previously, you had to have an interconnect in every USB area, plus, of course, associated exchange space, equipment, and backhaul, or some sort of agreement with the provider to do that for you. When chorus released tail extensions, suddenly it became a lot more accessible because you only needed 3 interconnects to cover the whole North Island. So you just needed Auckland, Hamilton, and Wellington. And I believe for the South Island it's only 2 interconnects, but I'd actually have to look that up. And then finally, cheap backhaul. So I think also in the last year or so, Chorus released a product called CRT, which is Chorus Regional Transport. And this brought the cost of a 10 gig DWDM kind of point-to-point fibre link down to around $4,000 a month, which is roughly $40 a megabit, obviously, if you're fully utilising the link. This lowered the national backhaul cost substantially, where previously you're probably paying a provider like FX Networks or now Vocus something like $5 a megabit. Obviously, you can't just use a single CRT link for your backhaul. You still need to have engineered redundancy, but the effect of these new products coming on stream was that the cost base dropped dramatically, and that actually made it affordable for smaller players to think about, hey look, maybe we can actually start doing our own chorus stuff. So what are the requirements, and where does SDN come in? Well, lower cost structures and acquiring tails help, but that's not enough. You still need exchange space, you still need hardware, you need software. For us, exchange space was easy. We have a really good relationship with 2 Degrees Enterprise, and they were able to sell us space in their chorus racks by the rack unit. So that helped out considerably in terms of deploying footprint. We didn't have to spend tens of thousands of dollars going in. We could just pay a few $100s per month for the amount of space required in the exchanges. Hardware, however, was the tricky and I guess fun part. As you probably all know, vendor gear, especially when I talk about vendor gear, I'm talking about your traditional vendors. So Juniper, Cisco, those guys. So vendor gear is expensive and it's often low density. So for us, we wanted a small footprint. We wanted to just go in with 1 RU. We wanted high port density, so 16 10 gig ports. We needed 48 volt DC telco power for exchanges. And we wanted to run converged infrastructure. So one box that was switch, router, BRAS, radius, DNS, etc. And it needed to be relatively cost effective. It needed to be cheap, comparatively. So building your own SDN appliance. And what is SDN? Well, to me, SDN, it's a bit of a marketing term, right? It feels a little bit like cloud. It's kind of whatever you want it to be. But for us, or for me, it's a combination of virtualized networking in the form of virtual routers combined with virtual switching and associated virtualized applications. So like your radius servers, your DNS, etc., all running on the same converged hardware. Now, in my personal experience, traditional vendors like Juniper and Cisco have done a bad job of producing virtual routing software for converged hardware. Generally, they only support older OS or hypervisor versions. They require quite specific hardware, Often they'll require specific driver patches, and the net result of kind of using the SDN products is that you've replaced a dedicated box from your traditional vendor with dedicated hardware to run SDN only for that vendor. So you've just kind of replaced one vendor box with another vendor box. You didn't really achieve anything. You don't really get that nice conversion infrastructure where you can kind of run everything alongside itself. So our SDN environment, the hardware. So it turns out finding virtualization hardware for exchanges is hard. 48-volt telco power is a real pain. You can't just take the standard equipment you use in the data center and shove it into a Chorus exchange. So initially, when we were getting things up and running, we actually needed to provide some services before we'd actually finalized all our hardware. And stuff was sitting on the boat or on the FedEx, or actually I think it took maybe 6 weeks for our contract manufacturers to actually manufacture our equipment. So as an interim step, we actually modified some MikroTik CHR 1016s. You see one here. It's actually sitting in the Napier Exchange today, actually still shifting packets. And that one has been modified for 48-volt telco power, where we've actually ripped out the 2 AC power supplies, and that's been replaced with 48-volt mean-well power supplies. And then on the front, some nice connectors have been installed, and yeah, that was kind of our interim solution. So onto our SDN hardware. I was really fortunate. I have a friend called Craig, and Craig was going through a similar exercise with a ISP that he works for, and they were actually looking at their own SDN platform, and they were actually looking at running Alcatel-Lucent SROS virtualized for doing a similar thing to what we're doing. So he'd done a bunch of the legwork. He'd gone to a few Chinese, Taiwanese manufacturers, brought some gear, and he said, hey, look at these guys in Taiwan called Lenna. They produce some half-decent kit. And so we ended up talking to them and going with a product from Lenna called the NCA 5510. It ticked all the boxes for us. It had 48-volt DC power. It was 1 RU. In the front there's actually no cards installed, but you can see that there's 4 slots there. So you install network modules in there, and you can stick a 4x10 gig card in that. So you can stick up to 16 10 gig cards. You can also get other modules for 1 gig, you get modules for 40 gig, and you can get modules for doing things like crypto acceleration as well. And you can stick more RAM in it than we needed, and a couple of SSDs if you want. And it had IPMI, or out-of-band management. Out-of-band management is actually really important when you're doing this kind of stuff, particularly when you're working with experimental hardware, experimental software. Eventually you're gonna screw it up, or you're gonna do an update, and you're gonna brick something somehow, and you kind of, when it's in the data center, it's not so bad. You can normally get in the car, drive down to the data center, or be there at 4 AM and do your changes. When it's in a Chorus exchange and you have to book downers, or it's in another part of the country, having out-of-band is a really critical requirement, particularly for serviceability of your infrastructure. So in our case, our build, we used Xeon E5 2640. That gave us 10 2.4 gig cores. The unit itself had a 95-watt TDP limit, so that was about the fastest CPU we could stick in there. We stuck 64 gigs of RAM in, and a single Intel Data Center Series SSD. And depending on where we were deploying these around the country, we used between 4 and 16 10 gig ports in terms of the modules that you can install. So I'll just grab and there's a closer view of the hardware. So you can see in the front there, you've got 2 10 gig cards installed, and you can just pop the covers off, slide new cards in, SSD on the side, in the back CPU and RAM, and then a couple of power supplies. There is also a PCI card at the back, although we don't actually use that. So the SDN environment, the software side. So in terms of software, we decided to run Proxmox VE 5, and that gave us virtualization with KVM and QEMU. It's a great Linux hypervisor that is an easy to use out-of-the-box package. So, if you're looking for something to ladder off and you don't really want to build your own, assemble all the parts, you can go off the shelf, you can buy this product. It starts at like $70 a year, and you can also buy versions with commercial support if you want as well. So, if you're used to VMware, you can kind of jump in with that and get going. However, it does run on pretty much standard Debian. So when you're starting to do funky things with your hypervisor environment, it's really easy to modify. It's not like VMware where you get a lot less access to the hypervisor. OpenvSwitch is the next kind of part of the SDN equation. OpenvSwitch is awesome. If you've never used OpenvSwitch before, particularly if you're coming from maybe a world where you've mainly just used VMware and standard switching or distributed virtual switching, go have a play with OpenvSwitch. Essentially, it allows you to take all of the network ports that you saw on the front of those boxes, so you've got your 16 10 gig ports, and turn them all into ports in a virtual switch. So similar commands to if you're working with a Cisco or a Juniper, but now it's internal to your virtualization environment. So that means that your NICs become switch ports, you can have access ports, you can have trunk ports, you can have Q and Q ports, you can actually have multiple virtual switches with different ports to different virtual switches. You can have switch ports between switches, and yeah, you can do some cool stuff in there. And we're really using it in the basic configuration. We're only scratching the surface with OpenvSwitch. But if you haven't played with it and you're working in networking, I'd really encourage you to have a look at it. And then for routing, and we are at MUM, so we chose MikroTik CHR. So CHR is great. It runs on everything. So you can run it on VMware, you can run it on KVM, you can probably run it on Zen. I haven't tried, but it just works. And there are no specific requirements, in terms of you can only use this particular hardware or this particular network card. You can actually run it in a converged environment. So, you're not having to run hardware, like say you're looking at Juniper VMX and then you're running a 3-year-old version of Ubuntu because that's the only thing they support, but then you actually want to run some modern packages and other bits and pieces. So you don't have those constraints. So yeah, kind of hat off to MikroTik for actually developing that product. It does what it says on the box, it works well. In terms of our particular requirements, it did VLANs and it has Q and Q support. And in some of the way we've architected the network, sometimes we're even using multiple, like more than 2 layers of Q and Q, so you've got Q and Q and Q in different parts here and there, coming off switches and things and exchanges. It does OSPF, it does our bridging, it does MPLS, VPLS, and you can DBRAS. And finally, a very important point, it is affordable. You can get a CHR license that's 10 gig for like $100 and something. If you go to a Cisco or a Juniper, their virtual product, and there is definitely a market for them, but it's the price of a small car, plus licensing for per user for applications like BRAS. So MikroTik kind of ticked all the boxes there. So some testing before deploying the equipment. We needed to do some testing, and actually I believe at this point most of our gear was actually in production in Taiwan, because when you're buying this and you're dealing directly with the OEM, they don't just have stock sitting around. You have to wait for the particular parts to get into a manufacturing cycle. Thankfully, I managed to get hold of some pre-production gear, and yeah, I'm doing some testing on the living room table. My flatmates love me. I sat there for the weekend learning how to build OpenvSwitch with that thing whirring away, and then doing bits of performance testing. And we're building OpenvSwitch from source to get the latest features at that time, so we kind of weren't too sure, is it actually going to work? What's performance going to be like? We kind of had no idea, but we'd ordered all the kit anyway, so we hoped it worked. So yeah, some testing. The optics worked. OpenvSwitch worked the way we thought it did. I'm not 100% sure of these numbers because this was almost a year ago now, and but at the time we did some performance testing, and I think from memory, doing about 1 gig of VPLS traffic in and out using the CCRs that you saw there, we were using about 10% of 1 CPU core. And so we're like, okay, cool, 10% of 1 CPU core, we've got 10 cores. We're never going to need 100 gigs out of this box anyway, but if we're getting half decent, it'll at least do multiple tens of gigabits, so should be all right. And yeah, Q and Q works, so yeah, great success. Packets flowed, etc. So yeah, that's my my kind of initial test rig there with a couple of CCRs that we were using just to test multiple levels of VLANs, making sure they're passing through, getting to the CCR, and then also doing some traffic generation on those and setting up some test VPLS circuits and just making sure stuff worked. So, exchange and handover time. If you've never worked with Chorus before, turns out Chorus is actually really complicated. There are so many portals, like there are 7 or 8 different portals, and they all have different authentication backends. So I think of the 7 or 8 portals up there, probably there's 4 or 5 different authentication backends. Your password changes every month. They all have different password complexity requirements. Some of them are, If you haven't worked with Chorus before, it is quite a lot of work, and each one of those portals has specific products, and inside that there's like 50-page training manuals on them. So if you've never touched this before, we're kind of in the deep end a little bit. Some of the challenges that we had. So we wanted to put a router in Merrill Drive because it was close to the city, and Merrill Drive was one of the, you could either be Merrill Drive, Mount Eden, or you could be Northcote, or I'm trying to think, not Green Heights. Anyway, one of the places on the shore, Glenfield, I think. So for a 10 gig handover in Auckland, Merrill Drive was the place we wanted to be. We also wanted to run a bunch of DFAS ports for our corporate clients in Auckland City, but MDR had no 10 gig handover ports left. So we actually ended up getting a 10 gig UFB handover in Mount Eden, and then having Chorus DFAS that back to MDR as part of a Chorus customer solution. One of the other challenges we found is that 1 gig BIDI optics didn't work very well on 10 gig cards. Turns out the Intel 10 gig cards, they're super picky. There are some 1 gig optics you can use, but the list is very limited. You can faff around, you can enable unsupported mode and kind of boot your machine with all these extra command line options from your bootloader to try and get unsupported mode working. It looked like it worked when we tested it, but when we actually got the box installed in MDR, it didn't work very well. And unfortunately, we did need 1 gig because we'd ordered what Chorus call a shared handover, which is your ADSL and VDSL products, and that was on a 1 gig BIDI. So in the end, our solution, after a lot of mucking around, our solution was just to FedEx in a 1 gig network module and pop that in there, and that solved our problem. Unfortunately, the 1 gig module actually killed our DDM, so it makes it a little bit harder if something breaks, but everything's working and we're just using it for that one handover. Some other challenges, everything crashed at one point, so that was particularly great. We actually did have some early production traffic running on this, and as you probably know, when your network's crashed, everything's on fire, it's really hard to diagnose stuff when everything's broken, particularly if everything's broken and you've got customers offline, and you don't always have time to run through all the logs and check every individual thing and try and actually work out why. What we found with that particular crash is it appeared to be, although we're not 100% sure, it appeared to be an issue with the Virt.io driver and the kernel. And in our case, the hypervisor itself didn't crash completely. What actually happened is it stopped passing traffic from the vSwitch into the MikroTik VM itself. The VM was running, the console was up, the interfaces were up. You could kind of up MAC addresses, but no traffic was moving. In the end, a reboot fixed it, and we updated our OpenvSwitch version, we updated our kernels, we deployed the latest MikroTik router OS, and the problem went away, it never resurfaced, so yeah, is what it is. Yeah. So, next part, EUBA and WVS is a pain. So EUBA, if you're not familiar with the term, is Chorus's term for ADSL. WVS is Chorus's term for VDSL, particularly EUBA using PPPoA. And that's how we lead into dealing with Q&Q handovers. So from Chorus, each customer tail, so each connection you have, comes in as Q&Q, or in some of our case, Q and Q and Q, just because of some of the architectures we were running. OpenvSwitch, Q&Q, doesn't use the right ether type. I use that term loosely. It uses ether type OX88A8. Most of the industry uses 8100. Technically, they're following the standard, but most people, when you're deploying Q&Q, you're just stacking 8100 tags. So you're stacking your standard 8021Q. So it turned out we couldn't actually use Q&Q very nicely inside our infrastructure. It would have sort of worked, but not really. So what we did in this case is we separated every handover into its own vSwitch for collision avoidance. So where that's important is, say you've got a couple of USB handovers on a box, otherwise you'll have SVIDs that will collide with each other, or say you've got a USB handover and a shared handover for ADSL and VDSL, and you'll get your SVIDs and your CVIDs, your VLANs will collide. So the way we got around that, because we couldn't use Q&Q, was actually just to spin up individual vSwitch and put the port that was running each Chorus interface into its own vSwitch. And then from there, each vSwitch has a port into the MikroTik virtual CHR we're running. So part two of this, I kind of explained that a little bit. So Q&Q means you have an SVID or an outer tag and a CVID, the inner tag for each circuit or tail. In our case, we were connecting each tail or CVID to a bridge for a specific reseller. So I wasn't actually just building this network for my own personal use. I was actually building this for like real other reseller type customers to use. So yep, we have to bridge out the CVID to an individual bridge for each customer, and then we use split horizon bridging to prevent the tails from talking to each other. So that's really important. You don't want customer on UFB connection A to talk to customer on UFB connection B, or so on and so forth. And also, Chorus does run some form of loop detection on their network. So if you bridge two tails just directly together, Chorus will just shut both tails down. I assume that's probably because, you know, the competencies of some of the fiber techs out there, and at some point, I'm sure they've spliced two customer tails together and made a loop in the network. So from there, once we've got our SVID interfaces, we've got our CVID interfaces, we've bridged out the CVID for the particular customer into a bridge, and then we're connecting that bridge to a VPLS circuit for each reseller, and we're VPLSing that back to a data center POP where our reseller then has a handover port, and then they have their own VRAS and do their own termination. So that makes it really easy for the resellers, because in this case, now they don't have to worry about Q and Q and what ports things are coming in on. They just get one port with a VLAN trunk, and that's got all their tails on it, and they just, you know, use their PPPoE VRAS. So we've got some resellers who are doing PPPoE on a CHR, some of them who are doing them on CCRs and other various bits of equipment. So some challenges with our design. Each customer circuit has to be built manually. So that means each SVID interface, each CVID interface, each bridge port, you're going to have to go in there, you're going to have to manually configure it. UFB is relatively easy. SVIDs and CVIDs are sequentially allocated based on when you order the circuit. EUBA and WVS, or AD-cell, VD-cell, they're not so easy. The SVIDs are kind of sort of allocated sequentially, so you'll get SVIDs that are like 1, 2, 3, 4, 5 to 29, and then suddenly it'll be 1236. And then every CVID for that individual customer tail is based on like the line card position of the customer on the actual equipment out in the field. So line cards explode, lightning strikes happen, Chorus come along, they'll swap out a line card, your CVIDs will change. And of course, because you've built all of this manually, you can kind of see the problem here. Chorus will replace the line card, now those particular customers are offline and you've got to go back and fix that. EUBA is even worse. So using PPPoE and VLAN 10 on EUBA, you get the assigned CVID by Chorus. So when you place the order on the Chorus portal, the CVID and SVID they tell you you have, that's actually what turns up on your handover. But if your customer dials PPPoE, it doesn't work like that. If they dial PPPoE, you get the CVID plus 1600. So if they were on CVID 30, they're now coming through on CVID 1630. And most shitty customer modems use PPPoE, even though some of them can do PPPoE. And we also have customers who use PPPoE and some who use PPPoE so they can do Ethernet bridging and other tricks. So you can't just go, oh, all ADSLs are going to be PPPoE. So that makes it, again, tricky because you have to either know what the customer's going to use or you have to build for both. So yeah, just another complication. So some future design improvements to what we did. We'd like to get more performance using OpenvSwitch and DPDK. DPDK is Intel technology, I believe, which is data plane development kit, and it allows the vSwitch to offload some of the networking to the network cards themselves. So it's kind of a little bit like FastPath or FastPath-like performance for x86 stuff, and actually have the time to go back and do some proper benchmarking. We did some benchmarking originally and went, yep, it looks cool, let's deploy it into production, but it would actually like some time to spend in the lab actually testing all the different configurations and what the performance is like. Your performance is going to vary vastly depending on what your payload is. So things like VPLS are going to be really fast, you're going to get really good performance. If you have a router in there and it's maybe got a full route table attached, packet forwarding performance isn't going to be so good. We are actually working on a custom build of OpenvSwitch that we need to do some testing on, where we actually hack out the 88A8 tag and we put in the 8100 tag so we can actually use Q and Q properly and actually spend a bit of time and actually test that. We want to make the LCD on the front of the appliance do something. At the moment, it just sits there blank. So we were going to have it tell kind of internet-related jokes. And then one of the things that we are now starting to deploy is hosted infrastructure for resellers. So in this case, if you're a small provider, you maybe don't have all of the cash to go out and build this yourself. We did it considerably cheaper than I think anyone else has done it, based on how we approach the problem. But we still sunk a pretty decent amount of cash into this. So the option here is that if you're a reseller, you could go out and pay the 10 grand bonds chorus, get your own handovers, but then instead of deploying all of the infrastructure and all the backhaul, you can just use our infrastructure, and we can host, for example, virtual routers on our infrastructure for you. So that's kind of like a nice kind of middle position. And the thing that I'm really excited about is dynamic VLAN creation. So that's kind of a bit of a result of being at NZNOG, drinking a lot of beer, and talking to the guys from WAND. I think it's the Waikato University's Advanced Networking Group. At NZNOG, we had a chat to them about some of these problems, talked about how we might be able to solve them using OpenFlow, and that leads into this. So this is something, admittedly, I don't have that much spare time, so this is something that WAND are working on for us, and it's dynamic VLAN creation. Essentially, our SVIDs and CVIDs, they come in the handover on the left there, and they go onto a vSwitch. If it's an existing SVID and CVID that's already been built, then that'll just go to where it needs to go. So, for example, the reseller bridge A for reseller A, because we've already built that, and then onto their VPLS to their handover or BRAS or whatever. However, if it's unknown traffic, we then forward it over to a magical kind of OpenFlow black box or script. And for all unknown traffic that arrives that doesn't have a CVID and SVID built, that'll look for a PPPoE discovery packet inside the CVID. And when it finds a PPPoE discovery packet inside the CVID, what will happen is it will bridge that CVID to a temporary PPPoE server or VM that sits on the box in the in the Chorus Exchange. What will then happen is the end client will try and establish a PPPoE session, and that session will get rejected, but as part of that incoming PPPoE session, we'll be able to see the realm. So we'll be able to see the domain name that the client's authenticating at, user at ISPA, and then from there, we can notify that domain or that realm back to the magical OpenFlow script, and that'll go, cool, we now know this CVID and SVID is attached to this particular reseller. And so we can then dynamically build the CVID and SVID to the correct bridge for that reseller. And so that gets around our problem of having to manually build SVIDs and CVIDs, and it also gets around all the problems we have when things like line cards get replaced. You could technically build a bunch more automation using Chorus's various portals and APIs, but that doesn't cover every particular edge case. And then, for example, when Chorus do like VLAN reassignment or remapping, they send you like an email with a CSV attached. So it's not that easy to automate that kind of stuff. So it's a lot easier to just make the majority of your connections assigned dynamically. Now, I guess one of the arguments here is if you did go to Juniper, pay the tens of thousands of dollars for an MX80 or their SDN appliance, they will do that to an extent. But in our case, we did actually try that, and we couldn't actually make it work on our particular hardware. So we decided to do it this way, and then actually just build the solution out of some open source technologies, which then don't cost us anything to license or use going forward. The other main advantage that we got with this, and I'm just going to flick to a view of some of our appliances there, is if, for example, you went out and did the traditional thing, maybe you just brought a MX80 and put them regionally around the country from Juniper, you'd be spending tens of thousands of dollars on one of those boxes. And you get 8 10 gig ports and 2 U of density. So in this case, we're getting up to 16 10 gig ports and 1 U of density, and we're building each box for around the $7,000 mark. So there's significant savings there. So what you see there, the image at the top is our Lenna appliance doing SDN with virtual MikroTiks on it in the Merrill Drive Exchange. It's a bunch of 10 gig ports in the first 3 cards, and then the last card is a 1 gig card. In the middle there, same thing in Wellington. In Wellington, we just have a 10 gig handover and a backhaul, and then the one at the bottom is in Napier. Technically, we don't need Napier to actually achieve coverage of the North Island, but we do have a bunch of customers down there, and we also have some other things like unison handovers. And there's a 52-port Arista switch that's actually cropped out of the image there, so we have quite a few fiber connections in Napier to support our customers down there. So the end product, we ended up with Chorus handovers in Auckland, Hamilton, and Wellington to cover the country, plus Napier because we needed to be there anyway. We ended up putting on a Unison handover in Napier. Unison are a local fibre company. They do everything very similar to the way Chorus do it. They even use the same Alcatel ONTs, but the guys on the ground there, they have similar coverage to Chorus. And we have data centre POPs at 220 Queen Street, Sky Tower, and Vocus Albany. And so, yeah, that's sort of an illustration of the network we built. And we managed to build all of that for less than 100 grand, which I don't think it's too bad of an attempt. So yeah, that's my presentation. If you have any questions, feel free to hit me up on Twitter, or if you'd like to know any more specifics or you're interested in some of the work we're going forward. But yeah, otherwise, does anyone have any questions? No? Cool, okay, we can get on with the beer.